Imagine having a coding assistant that's, I don't know, 100 times faster than you. It never sleeps, and it can write literally thousands of lines of working code in the blink of an eye. I mean, it sounds like an absolute dream, right? But, well, here's the catch. How do you actually know if the code it wrote is safe? Today we are unpacking a really fascinating 2026 paper by Thomas Winninger, and it's called Steerability via Constraints, a substrate for scalable oversight of coding agents. We're going to look at exactly how we can safely manage these superhuman AI coders. And honestly, the answer might just lie in some of the oldest, most basic tools in software engineering.
So, this brings us to the ultimate bottleneck question of modern software engineering. If you treat your AI agent like an incredibly fast, highly capable, but ultimately kind of untrustworthy junior developer, how on earth do you review thousands of lines of its code? Because in high-stakes pipelines, our biggest problem is definitely no longer capability. We know the AI can write the code. Our actual problem? Verification.
Okay, let's dive into this. To solve this crazy bottleneck, we need what researchers call scalable oversight. Basically, this is the ability for humans, or even small trusted AI models, to effectively audit and supervise systems that generate output way faster than we can manually read it. If the AI is generating code at massive scale, we absolutely need an oversight mechanism that can keep up with that scale, and we can't be sacrificing security or quality to do it.
So here is our roadmap for today's explainer. First, the AI oversight bottleneck. Second, why prompts are not enough. Third, steering agents with constraints. Fourth, the 11 backdoor experiment. And fifth, solving the oversight asymmetry. Let's get right into it.
Section 1. The AI oversight bottleneck and how security risks actually creep in. I really want you to picture the terrifying reality of losing control of a massive codebase. And the thing is, it doesn't just happen all at once. It's a slow, creeping threat. As the AI adds more and more files, security risks quietly creep in. And the human review process? It becomes so unbelievably costly that teams just start rubber stamping the AI's output out of sheer exhaustion. But the root cause of all this chaos is actually context length. Neither humans nor AI models can hold an entire repository in their working memory at once. When you rely on loose natural language guidelines, they just naturally drift as the codebase scales. A lot of current agentic solutions out there, like the Model Context Protocol, they try to solve this by simply feeding the agent more data. They're essentially just saturating the AI's context window with raw payloads. But as we're going to see, giving the AI more stuff to read actually works totally against good engineering discipline.
Section 2. Why prompts are not enough and the limits of instructions.
Now, what's really interesting about this slide is that we need to totally bust a very prevalent myth in the AI community right now. It's this idea that we can just prompt engineer our way out of this massive security nightmare. Notice the stark contrast here between asking an AI nicely on the left versus mathematically preventing it from misbehaving on the right. Prompt-based steering is really just advisory. The model might honor your rules or, it might not. They are super prone to indirect prompt injections, and they simply don't stop a rogue agent from executing arbitrary scripts. But now look at substrate constraints on the right side. These are mandatory. They are fully verifiable. If the AI breaks a rule here, the system literally refuses to run or compile the code. It is basically the difference between giving a polite suggestion and building a physical wall.
Section 3. Steering agents with constraints, basically going back to basics. So the brilliant, totally back-to-basics argument that Winninger makes is that the boring, battle-tested software engineering tools we've been using for decades to manage huge human teams, those are the exact keys to controlling the AI of tomorrow. In Python, this shift to a constrained substrate is actually highly specific. Look at the table. In an unconstrained setup, you might just use plain typing and keep all your big architectural rules tucked away in some giant central markdown file. But in the constrained setup, we are using strict linters to catch security bugs before execution, we're using frozen data classes, and crucially, this is key, at the bottom, we move invariants, which are the strict rules of the code, out of that central file and directly into local module docstrings. By moving these rules locally, we are literally forcing the AI to comply with the contract right where the code is written. It makes the rules textually visible before the code ever even runs.
But the code substrate itself is really just one piece of the puzzle here. The system also physically restricts the agent by isolating the environment using virtual machines and network proxies. It even includes an intercepting inference proxy, which means every single prompt and response is fully inspected before delivery. And instead of using these heavy, ultra-complex agentic frameworks to give the AI context, they use a tiny 200-line command line tool. This CLI tool projects only the necessary function headers and doc strings straight to the agent. It is highly effective, it's incredibly lightweight, and best of all, it's fully inspectable by humans.
Moving to Section 4, the 11 backdoor experiment, and testing these constraints.
Okay, so we've got this beautifully constrained system. But how do we actually test if these constraints can catch a rogue AI injecting malicious code? The methodology here is rigorous and, honestly, fascinating. Step 1, they deliberately inserted 11 different backdoors into a 500-line Python pipeline, and these range from simple syntactic flaws to really complex multi-file global invariant violations. Step 2, instead of using some massive, expensive, state-of-the-art model to review the code, they just used a small 8 billion parameter model, specifically Gemma 4 E4B, as the reviewer. And finally, Step 3, they had this small model conduct very narrow function-by-function review passes. They basically wanted to see if a small, trusted model could reliably catch silent security flaws hiding deep within the codebase.
The results here are incredibly revealing. Look on the far left. The unconstrained baseline with no tools missed nearly half the backdoors. It caught only 54.5% of them. Ouch. When they added the CLI tool, recall jumped up to 81.8%. But here is the tension. When they applied the strict constraints but actually took away the CLI tool, the reviewer caught 81.8% of the backdoors. Sure, but the precision plummeted. The small reviewer model was totally overwhelmed by seeing all these invariants without a clear way to verify them, so it just started heavily over-flagging false positives.
But check this out. When they combined the strict constrained substrate with that lightweight CLI tool, the results were absolutely astounding. The small reviewer model achieved an incredible 90.9% recall rate. And perhaps more importantly, it restored precision back to a massive 95.7%. Basically, by forcing the code into a highly auditable constrained structure and giving the model exactly the local context it needed, a small, weak model successfully audited extremely dangerous code that it otherwise would have completely missed.
Finally, Section 5, solving the oversight asymmetry and scaling safe deployment. So what does this massive jump in detection actually mean for the future of deploying autonomous AI developers safely? Well, it turns out the protocol matters just as much as the substrate itself. A small AI model needs the right scaffolding, so it doesn't get overwhelmed. Using a multi-pass review prevents the model from just hyperfixating on the very first bug it sees. By having the reviewer model do one pass purely for self-consistency, a totally separate pass for input/output contracts, and then another one just for side effects, you perfectly split up its cognitive load. This is how it utilizes the structured substrate to its absolute maximum potential.
So the crucial takeaway here is summarized in this incredibly profound quote from the paper. Verification shifts from open-ended comprehension to bounded invariant checking. Just think about how powerful that is for a second. We don't actually need our reviewer, whether that's a human or a small AI, to perfectly comprehend the massive, open-ended intent of thousands of lines of AI-generated code. If we enforce strict boundaries from the start, we just need to verify that those specific mathematical and structural constraints aren't violated. It totally changes the game.
Which really leaves us with this final, kind of provocative thought. We are currently spending millions and millions of dollars on complex prompt-based agentic frameworks to try and somehow control AI. But if basic, battle-tested software engineering tools, things like strict linters, type checkers, and local doc strings, can fundamentally tame superhuman AI agents, what other solved problems in computer science are we needlessly reinventing right now? It is absolutely time to rethink our AI tooling stack and maybe, just maybe, get back to basics. Thanks so much for joining me on this explainer, and keep questioning the code.